Okay, so this is question 8 from section 8.1. And in 8.1, we're starting to look at sampling distributions and their relationship to an underlying distribution that's being sampled from. So if you have a population and you keep pulling samples of the same size, here it's going to end up being 50. So I keep sampling 50 10-gram samples, right? And if I do that for those 50, I find that the sample mean is 2.4 here. And we're going to talk about the relationship between the sampling distribution and the underlying population in all these questions. I think there's five or six parts to this question. Okay, so the first is part A is why is the sampling distribution of the sample mean approximately normal? And that's kind of a weird thing. You know, we're not told that the population is distributedly normal, but we know that the sample mean will end up being distributed approximately normal as long as the sample size is large enough. And our book that tells us if it's over 30, if it's 30 or more, then it's large enough for the sample mean to have a approximately normal distribution. So we can choose C. The sampling distribution is approximately normal because the sample size is large enough. Okay. If we had, five, the sample size was 5, then we couldn't assume that. So we got that right. Okay. What is the mean and standard deviation of the sampling distribution, assuming that the population just mean is 2 and the population standard deviation is the square root of 2. Okay, so here's where we look at the relationship between the mean of the sample distribution, sample mean distribution, and the underlying population mean. And we find that they're going to be the same. The means end up being the same. So the mean of the sample distribution will be 2, just like the population. And the standard deviation actually isn't the same, but if we take the population standard deviation and we divide by the square root of the sample size, we'll get it. So what the sample size really does is it keeps the same mean, but it shrinks the standard deviation because you're always dividing by the square root of some positive number. So here that's 50, right? Our sample size is 50 right there. So let me just do square root of, what was it, square root of 2 divided by the square root of 50. Yeah, there it is, 0.2. So it gives us 0.2. Okay. So that's an important point right there to notice that difference, right? The square root of 2 is going to be some number between, 1 point something, right? And the standard deviation of the sample mean distribution is much less. It's only 0.2. So it's normally distributed, but it's definitely hugged tighter to the mean than it is in the population. And what is the probability of a simple random 50 10-gram portion, a sample of 50 10-gram portions of food items resulting in a mean of at least 2.4 inset fragments? So what I tell students is we're going to use the StatCrunch calculator to do this, but it's really good if you have a sense. It's really good if you have a sense of if that's going to be a low probability or a high probability. So if you think about it, the mean is 2. This is a normal distribution, and the standard deviation for the sample mean distribution is only 0.2. So 2.2 2.4, that's like 2 standard deviations. This is having a sample that's 2 standard deviations above the mean. So that's going to be a pretty small, right? It's going to be a lower probability. So let's see. I open up my StatCrunch calculator. I go to the normal, because we know the sample mean is normally distributed based on the sample size. And the mean is 2. Standard deviation is 0.2. And we want to know what's the probability of getting a 50 grand sample that has a mean of higher than 2.4. And so, yeah, that's pretty low. That's what, about 2%. I'm going to take all these decimals. I'm not sure how many places they want us to round to. Looks like 4. Okay. So that is, I'm going to round at the 7. I'll round that up to 8. Okay. Good. Okay, now this is a really important concept. It'll continue through the chapters all the way to 9 and 10. The idea of, I took a sample. Is this, based on what I know about the population, is this usual or unusual? And here it's unusual because it's less than 5%. That's kind of what if you pull a sample and you get a result that you're expecting less than 5% of the time, that's kind of unusual. So we say that the result is unusual because its probability is small. In the last part, it says what might we conclude about this? Well, what happens is that if you pull samples that are so improbable or have very low probabilities, then you start to doubt whether the original mean is really what you thought it was going to be before. So we were told that the mean was 2, but pulling this sample and finding its mean has us kind of doubting that. So we either pulled like incredibly rare sample or the mean is wrong. So since the result is unusual, it is reasonable to conclude that population mean is higher than 2. And we have, since the result is unusual, it is not reasonable to conclude that the population mean is higher than 2. We're going to go with A, right? If the population mean is higher than 2, then that makes this more getting a population, the average of the sample mean, getting the sample mean at 2.4 is going to be result in a higher probability, which we're expecting. I wouldn't be so unusual. I hope that helps, right? This is the toughest part to get. Since the result is unusual, that has us doubting the mean that we were told for the population, the 2. And it might have us think that the population mean should actually be higher than 2. And that would make getting this 2.4 more reasonable or more expected. That's the kind of idea behind it. And that's an important idea. Like I said, it continues through the rest of this. So I hope that helps a little bit with this question. Definitely lots of parts to it. So I hope that helps.